So what we're going to talk about today is something we'll call EPIC. And EPIC is a very specific set of technologies that lay on top of RFID. And in certain applications, it's sort of untouched in what it can do. And other applications, it might not be of any interest to you. And we'll really try and make it clear, absolutely clear, what it does and where it's useful. And what we're doing here is we're, in a pretty methodical way, we're keeping track of where all the errors are and fixing them on the fly so that they never hit you or your customer. So with that said, okay, on the question side, we talked about this before, but now probably half the people that I said it to didn't hear it. You guys are on mute right now, just so we don't have a lot of bandwidth problems. Please enter your questions during the presentation. After the presentation is done, we'll get to all those questions and kind of go through them one at a time. And
there's a question button on your window, so you should just be able to click that and type them in.
All right, enjoy the show. So we're going to talk about how does communication work between things in a rather general way, and then we'll kind of look at RFID as simply a communications platform where you're talking between the reader and a tag. Basically, you're passing information between those two devices. And we'll talk about what the shortcomings of RFID are. And it's a fantastic technology. It's done a good job in the world, but there are certain things it's incapable of. And then we'll talk about where EPIC plays and what it does and the places where it can be very valuable. And we'll show you some demonstrations. We have been selling this now in the market for about 6 months, so it's deeply embedded in a lot of our products. And then we'll walk you through the products. Whoops. And Neil, that was the slide you were supposed to do. Sorry, I'll get my head together here.
Okay.
All right. So we're all used to communications, right? This is a communications link we're on right now. You know, we're all sitting in front of a camera with a microphone. There's a screen in front of us. Information is going from there through pipes all over the world, and then it's received. And that doesn't, there's certain rules. You have memory and data on one side, and you have memory and data on the other side, and they have to talk to each other. And we just show some examples here of various types of sources of information and various types of channels. And then we'll talk about these channels in more general terms. And if you're thinking about data, you can have corrupt data. You can have data that's gone missing. But whatever that data is, it's got problems, typically. No data is perfect. And then if you look at the communications channel itself, there's the signal degrades in the channel, there's noise in the channel. The channel is basically bad things, if you will.
I mean, the channel, and good example about the channel right now is obviously we've all been watching Perseverance and the landing on Mars, and that's 11 minutes at the speed of light away. So it's quite a bit of noise on that channel.
Yeah, actually, without kind of the mathematical techniques that we use here, none of that stuff would ever happen. So let's talk about RFID, because RFID is in effect a communications link between a little memory device with a tiny little bit of processing power, the RFID tag, and a reader. And then there's a channel between them. And let's talk about the RFID tag. It's not self-powered. So we have to, one of the beauties of this is that we can remotely power something. That's great, but it has limitations. It doesn't have much processing capability, has very, very little, if any, real true error management. So that's what the tag is. Then the return channel, obviously the tag doesn't have much juice in terms of transmission power. So there's not a strong signal, and it gets weaker as we go past, and there's a lot of noise in the world. There's other readers. There are radios, there are cell phones, there are microwaves, there are motors, and all of those things screw up our readers. On the read side, there isn't an error correction capability in Gen 2 V2. None. And there's really not a way that these readers, there's a rudimentary way. If you look at like a Miller 4, some of the link profiles, they have some ability to handle noise in the channel, but very little. And there's nothing that authenticates the data on the RFID tag. And we've all heard of things like bit flips and ghost tags and things like that. Those are all nice ways of saying the data on the tag is corrupt and we can't figure it out. So, Neil, why don't you walk through this one?
Yeah, so basically, a lot of the flaws that we see in RFID today come down to what we've been discussing here. So today in RFID, if there's a corruption at the tag level, the tag memory level, that is just not detected. And the bad thing for us as an industry is, this bad data, once it's sourced on a tag, because there's no way of detecting it, it just flows straight away through to our customers, and they're oblivious to it. And if you're an end customer, on the call today, I mean, you're getting some of that bad data, unfortunately. So that bad data can be literally sourced from the memory on the tag, or it could be, as we're discussing on the transmission side, that could actually be happening during the transmission. So the memory may be okay, but the data is getting mixed up on the transmission side due to some of the noises and noise on the channel that we were just discussing. So in effect, because there's no error correction of significance here at all in RFID, that any single error here just flows straight through to the customer, and it basically becomes a very brittle system. There's a single point of failure in this system, and if any single bit gets screwed up anywhere, whether it's on the memory or on the transmission, it's just through to the customer, guaranteed.
Right. So this is a point where it's reasonable to step back and say, okay, that's pretty harsh. And we would honestly say, yeah, but it is realistic. There is, it is a single point of failure system. A more interesting question is, when does this matter? And if you're in a business where you're generally seeing your tags okay, it's not a really noisy read environment, and you're in a system where an error every now and then doesn't matter. If I say to you, well, does an error 1 out of 1,000 times bother you? If you say no, Epic isn't for you. Don't, I mean, you can stay on because you're curious, but this really isn't going to be something that transforms what you can and can't do. If you're in a place where data really matters and being right really matters, this is a way where you can absolutely guarantee that what you're presenting to customers is the data meant to be on the tag. Not the data on the tag, but the data that was written on the tag. So you can experience several bit flips here and still figure out what was the data that was written on the tag 11 years ago. And that is what matters to some customers. It's those customers that we're focused on here.
Yeah, another way of thinking about it is, we have a very automated system here with RFID. It's meant to be, as hands-off as possible. But if all of a sudden, if errors are important to you, then you need to start putting some additional checks in to make sure this stuff doesn't get through. And sometimes that means manual intervention. If you're doing manual intervention, you've broken the whole reason we're using RFID. So, we've got to solve this stuff.
Okay, so practically speaking, if you're in a quiet read environment, RFID really reads pretty well. And we'll talk about what we mean when we say quiet. But if it's not full of electromagnetic noise, RFID is great. You put it in a noisy environment, not so good. Tags, the practical lifetime of a tag is not limited by the tag physical structure itself. It's limited because you get a bit that flips and your tag's done. And that's a problem in some industries. We find that these tags stay robust for 3 to 6 months, sometimes longer. And that's plenty for some applications. But if you need a tag to last 2 years or 10 years or 20 years, current RFID leaves you in a place where your customers are going to look at you and say, mathematically, you're coming up short. And RFID doesn't have any way of saying that actually is the data that you intended. And
we should point out the reason we're here and we're having this conversation because of this technology is because we were brought here, because we had customers complaining about this stuff. We didn't just go and say, "Oh, let's go and do this today." If you take a look at the list of applications that we have on the screen right now, these are some of the applications that we have been involved in, and some of these are the ones that have been literally complaining to us about some of the problems with RFID, cold chain, pharmaceuticals, which is clearly of high relevance today, hospitals, law enforcement. Law enforcement was one of the first ones that kind of put us in this direction. Military and government for obvious reasons. Avionics, you don't want bad data there. Just ask people on some of the aircraft recently that have been almost falling out of skies. Manufacturing of all kinds. So it doesn't have to be government and military, but anything where data matters, and it's important to have that data accurate and just not changing. If you want to read something, it needs to be accurate. This webinar is of interest to you.
Yeah. So Neil and I are kind of funny because I'm trying to make sure that we constrain this tightly to the people that it matters for. And Neil is properly pointing out that customers brought us here. And the reason that we're spending a fair amount of time saying who wouldn't be interested in this is that if you're tracking a pair of socks, this is of absolutely no value to you. The socks are only on the floor for a few months. If you lose a pair of socks, nothing really bad happens. You're really looking at an extremely high volume, very low cost industry. Ain't for you. And then there's a lot of other industries where that model of really pushing cost down relentlessly and ignoring the fact that there are real needs for accuracy of data and robustness of the tag lifetime, those markets we feel that we serve very well by pushing these concepts and pushing these ideas. Okay. Yeah.
Curtain opens.
Yeah, so let's talk about an architecture that is quite different. It is a fully blown error management system. And by error management, we mean it detects errors and it localizes errors and it fixes errors. And when it's all done, it certifies that the errors are fixed. And so in RFID, we don't talk about failure rates very much. We don't talk about reliability systems very much. This is effectively bringing sort of a telecommunications language and approach to the data of this world. We're also going to talk about how it's implemented, and we can do this natively within our readers, and that does very cool things. But we can also provide a lot of the benefit here to legacy readers. So if you've got an installed base of R420s or Zebra readers or whatever, and your customers are looking at you and saying, geez, I really don't like bit flips, there's a very cost-effective way leaving that equipment in place that we can fix that. This is standards compliant, and we worked very hard. At some level, these techniques have been around for a bit. They're used in telecommunications and aerospace. The problem that this industry has is we wanted to make sure that this is fully compliant with legacy readers and legacy tags so that we can live in an environment where sometimes you're looking at underwear and sometimes you're looking at, I don't know, the fuse from a nuclear weapon, and errors in one are completely different in magnitude than in the other. It's also backwards compatible, and those two kind of go together. And we'll show actually these things reading just fine in an environment of legacy equipment and tags and Epic tags. Okay, Neil, why don't you walk through some of the things that we can do here?
Yeah, so the technology we're discussing here has a number of benefits, and clearly we were brought to the party here because we were seeing customers that were concerned about errors, errors in transmission and on the memory of these chips, as we've been discussing. So fundamentally, the core benefit we went out to attack was correcting those errors and doing error correction. And as we got involved in the technology, we started to kind of fill out the additional benefits that actually come with this technology, and kind of grow those benefits. And so we get the additional lifetime out of these tags now because we're correcting these errors, we're fixing them. So all of a sudden, your tag that may have died after 2 years or 3 years, because we're discussing here not correcting single bit errors, but multiple bits of errors in the tags or in the transmission. We can now extend the lifetime of those tags, maybe improve the yield of your usage of those tags. And we also even communicate additional information that effectively give you a sense of the lifetime of that tag. How well is it performing? Is it behaving? Does it have any errors at all? Is it going downhill? So we can even provide that kind of information as well. So because we're now also being able to correct the transmission side of the world, what actually ends up happening here as well is we provide some additional levels of performance, particularly in the noisy environments that Joe was discussing. So all of a sudden, because we can fix errors that would normally just kill an RFID tag stone dead, and that transmission just fails, because we can now correct those, we can now start to see tags that are either further away or at least further away in these noisy environments that would otherwise be perceived as being corrupted. So we can now see those tags. So we can actually get increased performance, better visibility into that tag population. And then another thing we do with Epic is we actually have a customer key as part of the technology and as part of the solution. And this customer key, as the name implies, is unique to each customer. So this allows us to optionally provide some additional levels of security and privacy with the data that's stored on that tag. Don't have to do that, but it's there for you if you want to do. So we can effectively use the customer key not just to ensure that the Epic data is yours, but actually hide that data stored in the EPC or in the user memory or whichever memory we're protecting here. And make sure that only you can see that data. So if that's important to you, that's an optional capability available to you.
Okay.
Now, all of this kind of together means that what is traditionally a very brittle system with RFID, where a single error just stops the thing stone dead, if you were to apply RFID into technologies like blockchain or authentication or encryption, things that require accurate data for them to function. If you have a bit error on one of these RFID tags and the data gets through blockchain, either the blockchain breaks or the data that's stored on the blockchain becomes corrupt, the authentication breaks. So now with Epic, we can now apply RFID with full confidence into these other technologies that would otherwise be fairly brittle when used with RFID. So blockchain works, authentication works, encryption works. So all of these are some of the benefits that we're now seeing coming out of the application of this Epic technology.
Okay. Yeah, it is interesting. There's a lot of things, if we talk about advancements in RFID, that are being chatted about. Blockchain is one, encryption is another, that a single layer kills it. And it's not really stated by the community that, if you have a bit flip on an encrypted tag, the encrypted tag goes on forever. And that's an interesting concept, that we talk about stuff that a single error prevents it functioning, but we don't acknowledge that. Right, we do. Okay, so let's talk a little bit about performance here. And this is a different way of capturing this discussion. It is a little technical, and we're going to try to do our best to help you understand where does RFID do well and where does it struggle. So on the bottom here, we show bit error rates, and that probably sounds like foreign language perhaps, but that just means how often is a bit wrong in transmission. So the information is coming across the channel does its bad things to it, and periodically a bit gets messed up. And what we show here is perfect transmission, which is no bit errors, to 10% bit error rates. And what we see is that that blue line is a reader running fast. So when you think about readers and they say, I'm running 1,000 tags a second, that's the kind of mode that runs 1,000 tags a second. The one that's sensitive is the one that's brown, and that's the one that reads a couple hundred tags a second, but it sees more tags. And you can kind of see here how that works in very, very low noise environments where you've got a lot of signal. You go fast, and it's the fastest. As noise starts to get bigger, as in other words, as we go to the right on this, you see that the more sensitive noise mode is more robust to channel noise. And that is a very common feature of communication channels, that as you slow things down, you can get more information through in a noisy environment. So let's talk about, Epic has a few different things that it does. Actually, it has two. The one is that it absolutely guarantees the data that you receive is correct. So there's error correction for problems on the tag. That's what we call level 2. Level 2 is available for on readers from us, or you can get level 2. You can hang it after other readers. It does not change the speed of the reader, and whether or not the reader sees the tag is unchanged, because we're not touching transmission here. We're just fixing the tag, and we guarantee in our base codec, which has been out there for about 6 months, we guarantee data up to 4 bits being corrupted. Other codecs can get up to 15. Now, it's important to say error correction in the real world outside of RFID is typically used not to just fix errors on the data device, but more importantly, to fix errors in the channel. So now we show our bit error rate going up to 20%. And I draw an arrow here to show what error correction does. And if we look at standard RFID at about an 8% bit error rate, you've knocked the reader's capability down to about 10 reads per second. But if you bring in Epic can fix a lot of the received tags that are wrong. And when it does, it pops the read rate up. And so in a similar noise environment, you get faster reads. And in fact, we showed data here in a relatively noise-free environment where we're still seeing up to 30% increase in reader speed, just in a simple single tag read environment. In development, we have what we call level 6. And level 6 is an adaptive. It's quite clever the way it works, and it really senses the noise in the environment and changes the error correction protocols on the fly to adapt to that. And what it really does is it pushes out the reader capability to incredibly high bit error rates. So we can have as much as 40% of the data, even more actually, corrupt, and we can figure out what the data is on the tag and verify that the data is correct. So here we show a point at about 10 reads per second with a normal RFID reader, about 8% bit error rates. And again, if we turn Epic on L6, we can get back up into the above 100 tags per second at that signal to noise ratio. More importantly, though, there's a lot of channels that are really screwed up, and 10 tags per second actually is a reasonably fast read rate. And we can read that kind of speed in excess of 30% of the bits being screwed up in transmission. We'll show you, if this is in development, we have not commercialized this yet. We have definitely been demonstrating it, though. And we'll show you what does it look like. And so this is an experiment that you all will sympathize with if you worked with RFID. So what we've done here is we've got an antenna, and 9 meters away from the antenna at about the limit of read range for this particular tag, we've placed the tags. So we're reading the tags just fine. And then we take another antenna from another reader. That reader is putting out 33 dBm of power, 2 watts of RF power. It's a 9 dBIC antenna, so it's a focused beam, and we take that antenna 2 meters away and we point it right at the sensing antenna that's looking at these tags. So we're just adding a huge amount of jamming. If we flip that jamming signal on, those tags are gone, absolutely gone. RFID can't read them to save its life. You turn on L4 with the DRM feature on the reader, and we can still detect those tags. You take L6, whether DRM is on or off, we absolutely positively can detect that tag and verify that the data on the tag is correct. And these types of sort of wicked RF environment exist in factories. They exist in places where there's other readers. And the whole movement into DRM, this is a completely different, much more elegant way. And without getting into the math and technical stuff, this is a much more elegant way of solving the dense reader problem than DRM. So to give you another example of this, and this one is a little bit hard to explain, so I apologize in advance. But if you look at the green and red over there, on the x-axis is basically bits 1 through 128 for this tag. And so you can see, I don't know if you can actually see the individual pixels on this thing, but that's what that is. And we've read that tag about 100 times. And so each trace to the right is a read. Red means that the data in that bit is wrong on that read. And so that's what this transmission looks like. It's full of errors. None of those reads actually came through successfully to the reader. That's the kind of read environment that Epic could see and give you the right data. And remember, that red is all wrong. So in an environment where a lot of the data that's coming back to this poor reader is all screwed up, we sort through that and actually find the tag data. So,
yeah, add something to that, Joe. So, if you had, if you picture this for just a conventional non-Epic system, if you had a single red dot per line, per horizontal line there, one single bit of error, that tag would fail. That tag would not be read. We're
that's
reading
right.
with that, with 30% of errors time after time after time. And we're able to read those tags, recover this data accurately, and tell you that it has been accurately interpreted. So we know and we can guarantee that data going to you is accurate. We know it's accurate. You know it's accurate. And that's all basically through all the algorithms as part of the Epic solution.
Whoops, wrong way. So really quickly, again, we talked about different levels. Level 2 lets you say to your customer, the data that we report is the data that you meant to write on the tag, and it can extend tag lifetimes very, very meaningfully. So that's what level 2 does. Tag lifetimes can be extended a lot, and the data that you receive is absolutely right. L4 starts to get at fixing transmission errors also, and it's a fairly light level of transmission correction, provides a little bit of improvement speed. L6 is a very dramatic approach to error correction for the channel, and it really takes advantage of some of the unique quirks of RFID, so that we're basically finding data in channels with a hysterically high amount of noise. Okay, so Neil, why don't you walk through this?
Yeah, so where do these problems come from? What's the source of these errors? And if we're looking particularly at the memory corruption, there are many sources of this corruption, and the most frequent ones are surprisingly actually physical chip damage. And as we all know, these tags right there, they're very flexible, and there's a little chip on there, and the silicon is if you've seen a larger silicon chip, they're very, very brittle devices, and they kind of break, they snap, they crack. And you know, as a semiconductor guy in my history, I always thought that if one of the chips broke, it would just stop working. Surprisingly, depending on where that crack is, of course, a lot of the time they still work, except there is a crack and it goes through one of the memory cells, and that basically destroys the memory cell. And so when that memory cell is interpreted, it's interpreted incorrectly, you get a bit flip. And you know, I spent 8 years at Alien Technology managing their semiconductors there. This was by far the most frequent error or problem that we saw from customers. Memory leaks is kind of manifest in a similar way, because each of these memory cells are very simple memory cells, these EEPROM cells inside of these semiconductor components. You can just picture them like a big bucket of water, and there's a little hole in the bottom. And over time, the water you put in that bucket just leaks out, and that's just semiconductors. Now, hopefully, that hole's small enough that it holds enough charge that when you try to read that memory cell, there's still enough water in there to read that as a 1, and it's not empty and interpreted as a 0. Now, if the hole's too big, it's a memory leak, and you know, the charge, the water basically just drains away from the bucket, and you read the incorrect value from that memory cell. And that can happen for a variety of reasons. You know, tags, as I said, naturally will do that over time. Can be something called infant mortality in chips when you first get them, where that can manifest itself. But it can also manifest itself almost at any time during the lifetime of a tag. Then another problem is, you know, in noisy environments, as we discussed, so more of a transmission problem. So if you try to read a tag in a noisy environment, as we've been discussing and just showed you on the past couple of slides, you know, that's where EPIC can come into play as well. So just noise in the environment. The other big problem that we see a lot in our world of RFID is actually when the RFID chip, the RFID tag is programmed. And if the programming process doesn't deliver enough charge into the memory cell, then, you know, that bucket of water hasn't been filled up enough. And again, it's going to be misinterpreted. So that can happen because the RFID tag is going through the write zone far too quickly. So insufficient charge gets pumped into it, or literally the charge is just applied for insufficient time. And so just not enough charge gets in, and so the data is never going to be interpreted correctly. And again, in my past, I've seen a lot of that as well, probably second to the physical damage. So all of this, yeah, go ahead.
Yeah, I was just going to say, one of the things that's funny is that everyone that's on this webinar, you know, me, Neil, all of our guests, you're sitting at a piece of electronics that has memory, and that memory absolutely positively is full of bad cells and bad memory sectors. And so that's kind of part of what the world does, is we manage our memory so that if we're testing it, and if it's bad, we fix those errors. One of the funny things about RFID is, because we don't do that, we test our tags a lot, and we're not trying to change that part of the industry that's screaming out the volumes. But these high volume commodity products that sell for pennies quite often are tested, you know, 3 or 4 times. Same test, you know, does a cell work, is done at the die level, at the inlay level, at the converter level, the end customer gets it. They all run 100% test on it. And one of the things that's interesting is, if the memory, if people got used to the idea that, you know, you can have 1, 2, 3 errors on this thing, it happens fine, perhaps we could also take some cost out of just the manufacturing of these things.
Yeah. And the other point out of this is chips tags could fail at any time. Obviously, they tend to fail most frequently either at the very beginning or as they age, but they can fail at any time due to these reasons here. The physical one is an obvious one. I mean, you can just, if the tension's too tight on the roll as the tags are rolled onto the rolls, then, you know, that could cause it.
Yeah. Again, and we're going to try and be pragmatic and focus on who really needs this. our customers, when we really look at customers that have, you know, tens of millions of tags out there, it looks like we're not seeing any issue to speak of with data corruption until we're 3 to 6 months in. So, you know, if you're focused on the retail thing or things are moving through your system quickly, it's not such a big issue. So let's talk about, do customers care? And it's an interesting question. There are a lot of times when an error rate of 1 in 1,000 just doesn't matter. And, you know, what we're showing you here is a simulation. This is based on about 8,000 tags in the simulation. It's a random simulation. We assume that there's a constant failure rate in this, and that there's all of the cells are perfect on day one, and that there's no failures in the initial period, which is kind of what our customers have said. A constant failure rate is probably undercalls the error rate, because if you kind of watch how things work, that these kind of things wear out over time. So at 3 months, you're pretty clean, and you really don't need us at 3 months. You're looking at 12 months. You know, if errors matter, this was very, very high error rate. If you're counting things where a percent is not a big deal, it doesn't matter. But you're starting to pick up failures at about a year in. 5 years in, it starts to look pretty bad. And when we're talking about things tracking assets for a long period of time, it can become a really big problem. And if you're looking at extended tags, where you're really having a customer that says, I'd like to track something for 20 years, can you help me? An honest answer to them is no. And, you know, it's an awkward answer, but if you want to track something for a longer period of time, you need something that boosts the reliability and durability of these tags. And we'll make one note here. We're not going to dwell on it. You can talk about a tag health check. And in effect, what we allow is some grace in the errors, and we let you pick up 1, 2, 3 errors before you really have to care too much. And as soon as you get to errors that are getting toward our limits of correction, you simply rewrite the tag. And it's a very elegant way of effectively restarting the tag's lifetime. So if 3 years in, you picked up 3 errors, it's not the end of the world. You just rewrite it and you're good to go. So here's some demonstrations. Our staff told us that our demonstrations were way too long, so they're much shorter now. Okay, so the first one is we're just going to show you an enterprise reader that is a native L4 reader. And I don't know why this thing isn't going. Here it goes. So we're just going to read. You can see there's 26 tags in the field. This is reading as a legacy reader. Now, there's a lot more information that you can find here when you go Epic. This is actually a mixture of Epic tags and legacy tags. If you see, they're color coded now. So red tags, we've intentionally put so much corruption on this that we couldn't find a solution. So we correctly identify those as hopelessly screwed up. The second thing that you'll notice is that, and I have no idea why this thing periodically sticks. Well, I can just talk to it. You'll notice that the green tags, those are Epic tags. And those tags, we've resolved the correct data, and we've counted the number of errors. So if you look at the top, those are a set of Epic tags that have 0 errors in them. If you look down at the bottom, there's a different set of Epic tags, and we've intentionally populated with those with errors, but we fixed all of them. And I do not know.
You'll see, 4, 1, 3, 4 errors, but are being corrected in those tags real time, completely autonomously by the Epic solution for you, and those errors have been corrected for you.
Yeah, we're having a little technical difficulties here, but now we also have this in a handheld. Life in RFID doesn't work very well unless you have a handheld, and this basically does exactly the same thing. So you see, we're correcting tags. We're working in an environment that's got both legacy tags and Epic tags, and we discern which is which and correctly process both of them. And And that's the end of that one. Sorry that the demos were a little sticky. So I'm going to talk about this, and then Neil's going to talk about the specifics of how this actually works. Again, if all you care about is that the data on the tag is correct, you can deploy this with any reader in the world. You can deploy this in any current install. And basically what is happening is that we're changing the information that goes on the tag, and we're interpreting the information that comes off of the tag. And it's that simple. You use the same die, you use the same tag, you can use the same converter. You know, heaven knows we really treasure our relationship with converters. They're good folks. We don't want to take business away from them. You can still use them just as they are. Your end customer doesn't notice. Tag can be put in the same place, tags read the same way. On the back end, you can use one of our readers, and our reader natively figures out what's going on and produces a data stream that's correct. If you're using a legacy reader, we post-process that data, and we're still able to tell you, is that a legacy tag or is it an epic tag? If it's an epic tag, we correct it. But the key point here is you're not changing what your end customer sees or feels. The converter doesn't change. The guy who makes your inlay doesn't change. The folks that make your die doesn't change. Nothing changes. It's just for that end customer, the data is correct. And again, we want to make sure that we're not insulting anybody. In a lot of applications with RFID, the fact that the data is occasionally wrong doesn't matter. We're not here to fight that battle. But there are a lot of customers out there that the data really matters. And for them, that's who we want to serve here. So I'm going to turn it over to Neil, and he can talk a little bit about just, from a business process, how does this go through?
Yeah, and fundamentally, if we take a look at what we're showing here, we've got, the consumer, the end customer of the tags on the top left there, and we've got the converter on the top right. Anything that's color blue, basically, it doesn't change. So the business processes that you would normally go through with your favorite converter, you can continue to use those as we've been mentioning. So the only thing that changes is normally when you reach out to a converter and you ask for another 100,000 tags or 1 million tags, basically you give them a file with the data you want written to those tags. Maybe the file is a start number and an end number and it's serial. Maybe it's very simple, but effectively that's what you're giving them. So instead of giving them that data, you just basically pass that data through SensThys, and today we're doing that in our premises, but eventually there'll be just a cloud thing that you just log into and you do. But effectively all we do is we just input your whatever data you have. Basically we take your customer key. Again, this data can be unique to you, and we encode this with Epic, and we just provide that data file onto your converter for you. We don't see your business model with your converter. We don't see what you're paying for your tags. We don't care. We don't want to know. So we just basically provide the Epic data to your converter, and they just go off and encode the data as they normally would do. So we're not changing those processes at all. Now, that's one model. The other model is if you're not sourcing tags from a converter, then you can actually source the tags from SensThys, and we will basically provide the tags to you pre-encoded with your Epic data. So there's two different paths here to getting Epic onto your tags.
Okay, so I'll tell you, I think that was covered here. Yeah, you got ahead of yourself, man. So it's a couple different ways you can. I'll just bust through this and then we can get into questions. There are a couple different ways you can evaluate this. One of the ways is if you've got your own readers and you're kind of stuck. No, I shouldn't say stuck, but you like those readers, or you have an existing reader population you need to deal with. You can just pick up some Epic tags. I think instead of 500 Epic tags, we thought 50 was plenty. What you'll get from us is you'll get your own customer key, you'll get 50 tags, and you'll get some software that you can put into your into a computer, and you can take the data stream off of a Zebra or Motorola or a Impinj, and correct it. Or you can buy this eval kit, and the eval kit basically is got the reader that Neil has in its hand, and you get the Epic key and the tags with that. And that reader, it's kind of fun. We actually had it in the demo, but that reader you can switch Epic on and off with a simple switch. There's also an option, if you want, we can get you a handheld that's got level 2 native to it and get you some tags, and you can do the same demo with a handheld. And with that, I know this is a little bit longer webinar than we usually do, and because we're not together, it's not as funny and breezy. But it's hard to be funny when you're remote. But I think at this point, let's open this up for questions and see what questions we have from people.
Yeah,
I can figure out how to do this. There we go.
There's a Q&A button in the UI, then the user interface. Just go ahead and click that and type them in.
Okay, so we're going to start with some of the questions that are just on the particulars of it. So, is this standards compliant? And the answer is yes. So if you have G1096 or you've got a healthcare thing that you need to be compliant with, it's relatively easy for us to honor that compliance. Another question that we've had is, is there a way that you can retrofit the readers of other folks to get the advantage in high noise environments? And then it's not we're not trying to be cute. There just isn't a way for us to do that. So if you're looking for readers that operate in a really high sensitivity environment, for right now anyway, you'd have to buy that reader from us. Another question is, how does this all go down? And part of that's proprietary, a bunch of it's patented, but basically we put some additional information into the tag. So if you got 96 bits of information, we'll write 128 bits to the tag, that kind of thing. Okay. It seems the Epic changes pre-Epic and post-Epic in the list we provide to our converter. Is that correct? So the EPC does change. So basically, the customer has an EPC, and as Neil said, you provide that to us. If you want privacy, we'll use a customer key to just obscure everything, and we kind of blow up the ability for anybody else to read your tag. That data is provided to the converter, and then the converter provides the data to your end customer. Some people want sort of semi-open or open tags where you can still read the tag with a legacy reader that doesn't have any decoding capability, and that legacy reader just can't tell you whether the data is right or not. And we can do that too, but it absolutely positively changes what's written to the EPC. Will the video be?
Hold on, let me just clarify that a little bit. So, as far as the user is concerned, the end user, they don't see the EPC changing. They just see, I want this data coded, and what comes out of it is always their EPC. The only thing that changes is the EPC is guaranteed to be correct, or you're told there's so much corruption that there's 50 bits of errors and it's unreadable. So you're actually guaranteed to get that data. So what we're discussing here is what actually gets physically stored on the tag. We change that data, and we can either change that data in such a way that the EPC is completely obscured, or we can still add the additional Epic information and still make that 96 bits visible to a normal reader. So that in that way, you could argue, are we changing those 96 bits? You could argue then no, there's additional information being written to the tag in that case, but the 96 bits doesn't have to be changed.
Yeah, so I'm going to try and make that shorter and simpler. What the end customer sees is not changed. So as a follow-on question, we have a Mr. Intrepid on the call right now. He's thinking of questions in series, and they're popping up on the screen, which is kind of fun. So the next question is, so what if I have a barcode on my tag? What is information on the barcode? And the barcode is what the customer would see in the EPC. So let's really say, what does the customer see? The customer sees the EPC. That's it. If you were to actually, one of the funny things is if you were actually to look at what a barcode says, a barcode has error correction built into it. So a barcode, in fact, doesn't say what the barcode says. It has a bunch of extra information, and it goes through an interpreter and presents you the data on the backside, which is exactly what we're doing here. So what the customer sees either through the barcode or through the tag is the EPC. What's actually in the barcode and what's actually on the tag is some additional data to protect your customer. I think I answered Mr. Intrepid's next question. How is a tag encoding weak? I get sometimes that a tag won't encode, but how is the encoding weak causing it to have? Okay, so the easiest way to think of these cells is a bucket. And when you fill up the bucket with water, the water level gets to a certain point and you say the bucket's more full than it is empty. And a strong write, if you will, if you write a tag really well, you fill the bucket all the way up to the top, absolutely to the top. And the bucket can actually lose quite a bit of water before you might consider that bucket to be more empty than it is full. And a weak write, which is it's really actually pretty hard for these converters to detect, and sophisticated guys like Mulbauer and the Voyantic guys, they actually think about this stuff a lot. A weak write is if you write it and it just kind of gets to here, and it's not really a 0, and it reads like a 1, but it's not a super strong 1. And so that's when people talk about weak writes, they're talking about the bucket not being very full. And what happens is by the time the bucket's been transported to a customer, the bucket's leaked enough that it's turned into a 0. And so the customer reads the roll of 100,000 tags. They find one of these tags has one error on it, and they conclude the converter's a moron. And we're being a little bit tough on the industry. But that is a consequence of a single error system, is that a small error on the converter side looks like a full failure on the end customer side.
Yeah, another little bit of color on that is effectively the way any memory cell is interpreted by the chip is it looks at that water level, that charge level. Is it full? Is it? And basically, there's a middle part where the chip doesn't know whether it's a 1 because it's more closer to full, or it's almost empty, so it should be a 0. So it's not black and white, like I'm either completely full or completely empty. Every time you read a memory cell, it's always some fullness or emptiness. And if it's below maybe 40%, it's regarded as empty, it's a 0. If it's above 60%, it's regarded as full, it's a 1. If it's somewhere between 40 and 60%, the chip goes, whoop, I don't know. And sometimes you see tags being read, you'll see a tag being read and you'll see a bit going 1 0 1 0 0 1 at different times you read it. That's exactly why.
Yeah, so that's right. And we have, and our customers have had the situation of they're reading a tag, and the tag is going from this value to this value to this value to this value. And there's really funny stories in the real world of what happens when end customers see this, but the long and the short of it is it's not a real shining hour for our industry. So we don't think of any of our readers as being legacy. I mean, you're hurting our feelings. The answer is
legacy.
Sorry. Go ahead, Neil.
Can legacy SensThys readers be updated to EPIC with a firmware upgrade or a hardware change?
Right now, you can go on the website and it's a firmware update. Some readers, it's an easy update, really fast. Some of them we need to update the firmware on the RFID module itself, but all SensThys readers can be updated, and they ain't no charge with that.
Yep.
If you want to figure it out and actually use it, you'll need to buy some tags from us, but with a pretty small amount of money, you can take a SensThys reader and be error correcting in an afternoon.
Yep.
Okay, so I think we burnt through enough of your time. Again, we do want to make sure that we frame this in a way that doesn't seem like we're being excessively mean to a very successful industry. RFID is a wonderful industry. It's really cranking out high volume stuff in great ways. What we're focused on here is customers that have real needs for accurate data. And by that, we mean, if you have something go wrong, bad things happen, we're your guys, or we're the team trying to solve your problems. We guarantee data. That's a very significant thing. We can make tags live effectively forever. That's another thing that really matters if you're tracking something that has a useful life of 10 years. And in noisy environments, we can help you read tags that other readers are just plain and simple blind to. And, we can demonstrate that to you all day long. It's a lot of fun.
And I just want to emphasize, this is not a science project, folks. This is in production. You can put it on. If you've got a SensThys reader, you can upgrade your reader now. If you don't have a SensThys reader, we have the capability to enable you with level 2 in your software. And we have customers using this in anger today, particularly in pharmaceuticals. So this
It's such a British thing. They're using it in anger. Actually, they're really happy with it. And by the way, we forgot because we had some technical glitches here, but it's really useful for us to pull back and say, how did we achieve this, and why do we achieve this? And the why is we had customers come to us with a series of problems, and to our customers, when they're sharing problems with us and they're allowing us to ask all the stupid questions that we do, we really appreciate that. And the second thing is, how do we do this? And first of all, we'd like to give credit to the SensThys team. They worked really, really hard and very creatively about what is this problem and how do we fix it. We also need to give credit to Harish. Harish is a postdoc that works with us from Melbourne, Australia. It's a sweet guy and smart as a whip. And to him, it's really interesting to work with error correction in this world that's so different than what he's used to working in. And finally, really like to reach out to the team at MTI. We're constantly asking them to rewrite the inner logic of their reader modules. And not only do they humor us, but they come back with concrete suggestions about how to make this work and how to make it work really fast. So we're making all these crazy decisions fast enough that you don't even see the decision being made. So thank you to everybody there, starting with our customers and ending with the people that help. All right, with that, so I have to say that Neil has just been complimented for the brain dripping the blood out by one of our customers. With that, say good night, Neil.
Good night, Neil.
All right, bye, y'all.
Bye.